In Thursday's lecture, I introduced the ideas of direct and iterative methods, and then we talked about a very specific direct method called the Tomas algorithm that only works for tridiagonal matrices. These are matrices with the three main diagonals being mostly non-zero. So there's a main diagonal, upper diagonal, and lower diagonal. Immediately above and below the main diagonal, they're non-zero. And pardon me, there's a very beautiful and very efficient method called the Tomas algorithm. So we introduced that, gave you some examples in Python. And I also gave you examples on how to construct a full matrix using just only diagonals, using the diag function. Now, one may ask, well, for the Tomas algorithm, we only need the main diagonal, upper diagonal, and lower diagonal. Why are you constructing a full matrix with that? Well, it's because I'm going to ask you to compare your solution to the built-in solve method in Python. And the built-in solve method in Python requires a full matrix. Okay? So therefore, you need to be able to construct a full matrix. Okay? Just as a footnote if you're a little bit confused about that, or why we did that. Okay? Okay. Diagonal matrices in Python. And what I'm going to show you here next is, so over the years, when I first taught this class in 2017, I asked everyone to implement the Tomas algorithm, the Gauss-Seidel, and the Jacobi. Then last year, I kind of asked them to implement the Tomas algorithm, most of it, and I gave them the Gauss-Seidel and the Jacobi. But this year, I decided, hey, I'm just going to give you all of these codes, all of the routines. I may ask you to modify them a little bit in the hopes that, the question is, what type of user do you want to be of numerical methods? I personally never have to worry about implementing Tomas or like a Krylov method. I just use a library for that. But know for sure that when I was doing this, when I was learning this, I did implement the Tomas algorithm and the Jacobi method and the Gauss-Seidel. The lesson being is I learned how to program by doing these things, okay? I learned important concepts doing these things, okay? I tell you from now, you're not going to be using, this is probably the last time you'll see this algorithm, and then once you're off, you're going to be using a packaged library that does very efficient solution methods for you. But the fact that you spent time to read the implementation and understand it, that taught you something. That always stands for something, okay? It's going to be in your subconscious, like at some point I did this, and your brain memory is going to come up to the rescue at one point. Or not, but I'm hoping it will. Okay. Once we start putting this in a notebook, I'll explain to you what I'm doing here. But this is essentially a reproduction of the Tomas algorithm, with the only caveat that the way I'm showing the Tomas algorithm over here, it's based on indexing of 1. So we start indexing 1, 2, 3 to n. In Python, we index from 0 to n minus 1. So you have to shift everything by -1, okay? That's the only thing that you have to pay attention to. So when I tell you, go and run the Tomas algorithm on this matrix and whatever, when you implement the Tomas in your code or copy this, make sure you understand how I'm using the indexing, okay? So for example, the first step in the Tomas algorithm, you go from 2 to n, okay? Whereas over here, this is the first step, okay? For I in range, I'm going from 1 to n minus 1. Remember, range goes from 1 to the last entry minus 1. So rather than going from 2 to n, I'm going from 1 to n minus 1 because I shifted everything by 1, okay? Because Python operates as a 0 index, okay? Okay. What's interesting about this lecture today is to give you a serious example of where these tridiagonal matrices show up, okay? And I call this the TDMA series example, heat transfer in a rod, okay? So what I want you to consider now is a rod or a section of material. So you can think of this as, the side wall in this room. So there's a wall over here, and there's drywall, and there's probably inside some material or some air in it, okay? But imagine we're exposing the inside to a fixed temperature and the outside to another fixed temperature. But also, we are heating the rod or the section in the middle, somewhere in the middle. I created this cool animation here. So obviously what's going to happen, the rod is going to heat up, or the material is going to start heating up and heating up and heating up. But eventually it is going to reach a steady state. And you will learn this in heat transfer, where the heat flux, the rate of change of the heat flux becomes 0 across the rod. But then the temperature distribution, there's a different temperature at every point in the rod, right? You agree? Because there's a different temperature on the left, different temperature on the right, and there's heating happening in the middle, okay? Now, the equation governing this heat transfer is given by this formula. Second derivative of temperature with respect to x, so that's the rate of change of the temperature with respect to x, is equal to minus 1 over k times some source term. Now, T is the temperature. You're not responsible for knowing where this equation comes from. Okay, know that you will learn it at some point, and you're not going to be even responsible on how we discretize this equation. I want to illustrate a real process to you. Okay, you learn about this in heat transfer. But this is a true equation, steady state heat transfer. K is the thermal conductivity. Does anyone know what that means? So it's resistance. It's how much the material can resist heat transfer. So if you want a very well insulating material, you want to get a material with a very low thermal conductivity. The higher the thermal conductivity, the more thermal conductivity there is. So you put a temperature at one point with a high thermally conducting material, very quickly the other end of the material is going to sense that temperature, okay, or that heat. With a very low conductivity material, it's going to be hard, it's going to be more insulating. So air, for example, has a lower thermal conductivity than water, okay? So that's why we kind of boil things, right? Because, you transfer the heat from the range to the water, and then the water transfers the heat very effectively to the, to the thing you're cooking. Okay. Now, our goal is to find this temperature distribution numerically. Forget about exact solutions of ODEs and etc. You learned that in your partial differential on ODEs class. Over here, we want to solve this equation numerically, okay? Okay, so to solve this problem on a computer, we first need, because on computers we deal with arrays and things that are discrete, and I still have a laugh when I use the word discrete, because first lecture was, solving things discretely in a very discrete manner. Anyway, so the processes would be to subdivide the rod, or the object you're having, into a discrete set of points. So this is a finite number of points, okay? And you set that number of points. You say, I want 100 points, or 200 points, or 5 points, okay? And you just subdivide the rod into a finite number of points. In this example, we'll just illustrate with 5 points, okay, for simplicity, okay? And this is what it looks like, actually 6 points, or 5 intervals, or 6 points, okay? So I'm going to take this rod, and I'm going to place a point at the boundaries, and a point at the other boundary, and just subdivide things equally, okay? Now, the spacing, you can define that as delta x. We'll talk about this in a second. But what we're going to do numerically, we will then attach a temperature to each one of those points, a temperature value, okay? And that value, we don't know what it is, right? But I'm going to give it a name. I'm going to call those T0, T1, T2, T3, T4, T5, Don't call them TA, TB, TC, TD, TB. You're going to run out of letters, right? Because we're going to solve this for 1,000 points, okay? The more points we subdivide the rod into, the better our approximation is going to be, okay? Do you agree so far? So we assigned an unknown to each one of those points. Now pay attention to the boundaries, because in this particular setup, I'm giving you the temperature at the boundaries. So the temperatures at the boundaries, in other words, T0 and T5, they are known values. They're set by the user, the experimentalist, the engineer. Okay, we specify those values. Okay, so in effect, we really are looking for T1 through T4 in this case. Okay, and our goal is to find the temperature at those discrete points. Okay. Again, you will later learn how to convert a continuous ODE. Actually, in this class, by the end of class, we will learn how to convert this continuous ODE, second order ODE, into a discrete set of algebraic equations. Okay, but right now, don't worry about this. I will give you these equations. In your exam, in your homework, I'll be giving you those equations. Now, just for, stepping back for a second, with iterative methods, all you care about is knowing, linear solvers, all you care about is knowing the structure of the matrix. What is the matrix? What is the coefficient matrix, and what's the right-hand side, okay? But I'm showing you here some extra steps to kind of, spark your interest in how we get to these matrices. Okay, so taking this continuous ODE and turning it into a discrete set of equations is a process called discretization. Again, comes from the word discrete. And for a general mesh, you said, we did this for 6 points up there. If you do this for an arbitrary number of points, at any point I, an arbitrary point I, so it could be T1, T2, T3, whatever, this equation can be converted into this equation, okay? Don't worry about how we did this now. This is not a question for you to answer right now, okay? At the end of the semester, you will know how to do this, but know that we can do this. Notice the second derivative was converted into, second derivative at point I is converted into a linear relation between ti plus 1, ti, and ti minus 1, okay? And there's the delta x squared, and minus 1 over k, and there's this source term at point xi. We'll talk about this in a second, okay? Now I'm going to simplify this a little bit and write it in this form. Ti plus 1 minus 2ti plus ti minus 1. So at any point I, the heat transfer equation turns into a linear relation between the neighboring points and point I, between the temperatures at the neighboring points and point I, okay? So for example, for point 1, you simply put I equal 1. This gives you, this gives you T0 minus 2T1 plus T2 equal minus delta x squared S at x1 over k. For point 2, you get T1 minus 2T2 plus T3 and so on. So you can repeat this process for an arbitrary number of points. But we obviously need to define what we mean by Sx1, Sx2, or Sxi in general, okay? So just like we did with the temperature, now the temperature, yes?
So it doesn't matter that you switch the T sub I minus 1 to T sub I plus 1?
No, I just rearranged them. You can put you can move Ti minus 1, move Ti plus 1 over here. That's what I did, okay? Still the same thing, okay? Thank you. That startled me earlier. I was like, what? Why did I? But I like to order them kind of in correct order. Okay. Okay. So now, know that this is the case. Don't worry about how we got this. I'm going to give you these equations. Okay. So obviously we need to define S of x. What do we mean by S of xi? Just like we assigned a value for the temperature at each point, it just so happens that that temperature is an unknown. Our goal is to find T0, T1, and T2, okay? The same way we can assign a value for the coordinate, for the x coordinate on this grid, okay? So if you call this x equals 0 and this x equal L, and you subdivide this, to 5 intervals over here, then you can define x0, x1, x2, x3, and x4, right? Do you think you can do this? Well, let's say L is equal to 1. Then delta x is 1 over 5, right? Because we cut this rod into 5 intervals, okay? And starting with x0 equals 0, right? It's at the beginning of the rod. Then x1 is located at delta x, right? It's delta x away from x0. x2 is what? Delta x away from x1. So x2 is x1 plus delta x. That's equal to 2 delta x. x3 is delta x away from x2. So it's x2 plus delta x, and so on. It just becomes really repetitive. And then at the end point, you better make sure that you actually get x equal L with this formula. Indeed, it's x4 plus delta x. That's 5 delta x. That's 5 over 5 equal 1. Now, in Python, it's really quick. You can do this with one line of code using what's called linspace. Okay? So linspace, it generates a set of equally spaced points. You tell it the origin, the endpoint, so x0, xl, and how many points you want. So over here, I'm going to create a linspace, and it's from NumPy, by the way, going from 0 to L with endpoints. L is 1, n equal 5, and this is what we get. 0, so that's x0. This is x1, x2, x3, x4, for example. Okay? You can do 6 points, etc. Okay? Okay. Now, the source term, okay, so we defined xi now, right? We defined x1, x2, and so on. The same way we can define s of x as well, because s of x is a continuous function of x. And if we give x and discrete values, then that continuous function becomes discrete at those values. We can evaluate s of x at each one of those x's, okay, that we just defined. So for shorthand notation, I'm going to call si s of xi, just for simplicity. So s1 is s evaluated at x1. S2 is s evaluated at x2, and so on. Okay? Same thing. At each one of those grid points, there is an s. Okay? There is a value for s. And there's a typo over here. Okay, this is incorrect. This is just s0. Let me fix it right now. Okay. There's a typo right there. Okay. So s0 at x0, s1, s2, s4, etc. For example, if s was given to you, that's, you know, the heating source, it's e to the minus x squared. That's a continuous function in x. You can evaluate that at any value of x. It just happens we want to evaluate it at those discrete values. So s1 is at s at x1, and x1 we know that's equal to 0, right? In this case, or sorry, that's equal to delta x. So it will be e to the minus delta x squared. That's it. You know the value of x1, and you know the value of x2, and so on and so forth. Agreed? Okay, so how would we do this in Python? I've seen some go and manually evaluate s at x1, s at x2, s, etc., etc. Now think about the example with NumPy arrays. If we could create an array of x values, would NumPy allow us to pass that entire array into a function like exponential? Yeah. So the same way we define subtraction, multiplication, division, addition on NumPy arrays, we can apply a function on a NumPy array, and it will return a NumPy array where each entry is the function applied at each point. Okay? So let me show you how we do this. Again, you create a linear space for x. No, first you define your source term. In this case, let's say at 0.01 e to the minus x minus 0.5 squared. Okay? So that's a distribution, say some type of Gaussian distribution of heat along the rod. So it's centered at in the middle of the rod. The rod's length is 1, and there's 5 points. Then what you do, you define your x's as a linspace. You define x0, x1, x2, x3, x4, and so on. And then all you have to do is pass this NP linspace is an array of values, x0, x1, x2, x3, and so on. You pass that entire array to your function. S is equal source of x, of this guy. And then you print it, and then you get all of the values in one shot. Yes?
So going back to that S function, as you input x, isn't that x the distance from the heat source?
No.
Okay.
That's the absolute location in the coordinate system. No. It depends how you define your coordinate system. I mean, you can make it, you can change your coordinate system and put it centered on the source term, but that's horrible. It's going to be so complicated. That would just complicate everything. Okay? I mean, it's easier to just set it up this way. Okay? Because then you'd have to know where you are away from the source. What if I change the source location? Okay, so agreed. Do you see this? Do you see how we can do this now? Don't go and implement S of x0 and S of x1, etc. Just apply the function on the entire array. If it's a NumPy array, if your function is a NumPy function, now granted, you have to be careful here. I didn't use the exponential from the math module. If I use the exponential from the math module, it will throw an error, because the exponential from the math module is only defined for a single value, not for an array. So that's why when I go back and I tell you don't be ambiguous about your functions, use module dot, exponential to be clear, to know and to be clear on what function you're using, okay? So in this case, I'm using NumPy exponential, okay? So this will take an array and return an array, okay? Now that the coordinates have been and the source terms have been defined, we can finally get to defining the governing equations, okay? Again, for each one of the blue points, there is a linear equation that relates the temperature at the two neighboring points to the temperature at that point, okay? So for point 0, we know the temperature. We say T0 is equal to T left. That's the point, that's the temperature value specified by the user. You can specify that, the experimentalist can specify that. Let's say, this is like I don't know, you have your, you're roasting something on a fireplace, and there's like two temperatures at the end of the fireplace and where you're holding it, and there's heat coming in the middle. That's a scenario like this, okay? And you can fix the temperature using different methods, but, assuming now we know what the temperature is at T0, then at point 1, again, we just write down the equations. T0 minus 2T1 plus 2T2 is equal to this, and then same thing for point 2, point 3, point 4. You see how these become repetitive, okay? And wait until we put those in a matrix form, and that will be your aha moment, okay, if you haven't seen it yet. And then finally, for point 5, T5, or the last value of temperature, is equal to T right. That's the temperature given at the other end of the rod. Agreed so far? Okay. So again, do not worry about how these equations came about. You will learn about this when we study discretization of ODEs and PDEs. However, pay attention to the different form of the equation near at the boundaries, okay? T5 and T0. But over here, they're kind of systematically looking the same, okay? So now let's put this in matrix form. What do you think we're going to get? Lo and behold, we get a tridiagonal system of equations, okay, where we start with the unknown vector, T0 to T5. There's T0, T1, T2, T3, T4, T5. Let's start with the first equation. The first equation says 1 times T0 plus 0 T1 plus 0 T2, etc. So the first equation tells us T0 is equal to T0, or T left. Okay? There's a typo also over here. That's from the previous year's lecture. Always, okay, so let's call this T left. We'll call this T right, okay? Okay, so the first equation tells us T0 equal T left. Agreed? That's exactly what we had. The second equation, what is it? T0, remember, it's the dot product of this vector with that vector. So it's 1 T0 minus 2 T1 plus T2 plus 0 T3 plus 0 T4 plus 0 T5. So that gives us this equation, T0 minus 2 T1 plus T2 equal minus delta x squared times S1 over K. And so on. That's a real life application of how tridiagonal matrices show up. If you go to 2 dimensions, you get a pentadiagonal system. If you go to 3D, you get 7 diagonals, okay? Should show up before the matrix. Okay. Now what you should take from this is what the matrix looks like, because what happens now if I go to 8 points rather than 6 points? Okay, but would the coefficients change? No. Say that it just keeps expanding. What if we go to 1,000 points? Just become, okay, what is the size of the matrix for n points? n by n, because you have n equations and n unknowns. Granted, t0 and tn, the tn minus 1, the last point, they're known. We just put them in the matrix, okay? Just keep them in the matrix. Doesn't matter. So for an arbitrary number of points, the equation looks like this, always. The first equation is 1t0 equal t left, and the last equation is 1tn minus 1 equal tl. And everything is between is just 1s over here, minus 2s, and then 1s. Okay? It doesn't matter how many points you put. So with this general form, you should be able to do it for n equal 3, for n equal 6, for whatever n you want. Okay? Now, for your exams, there will not be programming questions on your exam. I'm not going to ask you any programming questions. All the questions will be theory, okay, and essentially trying to understand this. But one question I will ask you is, given these equations, write the system for 5 by 5, okay, for 5 points. So you should be able to reproduce this matrix, okay, and I'll give you enough details to reproduce the matrix, okay? So that's why I'm showing these examples. But for Python, you want to do this for an arbitrary number of points. And this is how we do it. So you define n. And remember, in my lecture, I told you we're going to use a built-in function in NumPy called ones. Okay? It generates an array of values equal to 1. And the way we construct a matrix like this is this lower diagonal, we create an array of ones, a vector of ones, and then fix this last value. For the upper diagonal, we create an array of ones and fix this first value. For the main diagonal, we create an array of ones. We multiply it by minus 2, because most of the entries are minus 2. And then we fix the first and last entries. Okay? And this is, and I showed you examples of this in Thursday's lecture. But this is a reminder of how this is done. So the main diagonal is minus 2 times 1. But what is the length of 1? It's n. There's n entries over here, right? And you define n ahead of time, n equal 5 in this case. And then you fix the first entry, d0 equal 1, and fix the last entry. And I discussed this notation, d minus 1 equal 1. What this notation means, Python allows you to index in the positive direction, so going from 0, 1, 2, 3, and also from the end. So if you want to access the last element, rather than saying, oh, what is the last element? Is it n minus 1 or n minus 2 or n? You just do minus 1, gives you the last element. Minus 2 gives you the second from last. Minus 3 gives you the third from last. Makes sense? It simplifies things. So you don't have to worry about what n is, okay? So this is what I'm doing here. D equal minus 2 times 1 n, it creates minus 2s everywhere, okay? And then d0 equal 1 fixes this value, and d minus 1 equal 1 fixes this value. U is my upper diagonal. It has length n minus 1, because it's one less equation, right, over here. There's n minus 1 entries. And it's all ones except for this guy. So that's u0 equals 0. Same thing for the lower diagonal. It's n minus 1 entries, but the last entry is 0, okay? And we fix it. All right, so let's try to do all of this in class and see. See, there's a slide here that says in class illustration, okay? So let's illustrate it in class, okay? Why don't you open up your Jupyter notebooks? We have just barely 10 minutes, so we'll try to get as much mileage as we can. Are you comfortable with the diag function and ones and, you know, creating these arrays from Thursday's lecture? Are you fairly familiar with those? Okay, because I'm just going to assume that you are, and we'll start using them to get to the tridiagonal solution, okay? Okay, so let's just delete everything over here. Okay, let's see. Okay, the first example I wanna give you is the example we did I guess we kind of covered by hand in Thursday's lecture. Okay, it was this example. Okay, remember this example? It was this matrix, and it was a tridiagonal matrix. Okay, sometimes you have to rearrange the equations so that they look tridiagonal. So be careful about that. You can rearrange your equations any way you like. It's just about ordering them to make them tridiagonal. Okay. So let's start by just using the Tomas algorithm and to solve this system and verify that our solution was, what was it? Hold on. The solution was 1, 2, 3, 4, right? So that was the solution. Just kind of 1, 2, 3, 4. Okay. So let's try to do this. And first thing I'm going to do is take this algorithm over here, this code, and paste it in a Jupyter notebook. So I'm going to declare this as a function. So import numpy as np. And again, think of the Tomas routine or the TDMA routine as a box that takes input and produces output. So what is the input? You can the diagonals, right? Because we don't want to store a full matrix. We argued against storing a full matrix. I mean, you can choose to give it a matrix. It's up to you. You're the programmer, and then pick the diagonals from the matrix. But it's faster and cheaper to just pass the diagonals. So we need the lower, main, and upper diagonals, and we also need the right-hand side, right? So that's what I have here: lower, main diagonal, upper diagonal, and the right-hand side. And what does the Tomas algorithm return? It returns a solution, okay? Returns X. So one other strategy I should have probably used here is to call the solution or result. Call it result, for example. Okay? Let's just call it result. It's up to you what you want to call it, because you can get confused between X and Y and X and Z. Yes?
If one is always the lower, why do we need to define it in the
It's not always the lower. Remember, the Tomas algorithm. Yes, it's an L. Yeah, sorry. Okay, that's a good point. Yeah, that's an L. You can probably use a capital letter. It's one of the failings of typography. Okay, now you can probably pick this whole thing up from the PDF on my website. Just go there. It's posted. The code, the PDF, the code in the PDF is posted, so you can just copy and paste it in your Jupyter notebook, or you can copy it from here. I will leave it up to you to study what I'm doing here, okay? And if you have questions, you can ask the TAs on how we did this, but it's really straightforward. I need a number of equations, so I get that from the size of one of the main diagonal, and then I declare a result value which will store the answers for me, and it's going to be of size n, and I fill it with zeros, and then I implement the 2 steps of the Tomas algorithm, starting with step 1, going from 1 to n minus 1. Remember, range starts from 1 to n minus 1, and then just implement the formulas we had in class, and then the step 2 start at the end, which is result n minus 1, or you can do result minus 1 to start at the last entry, and then bn minus 1 over dn minus 1, and then you loop from the last entry, which is n minus 2, to 0, right, because we're indexed at 0, and you decrement by minus 1. So this is saying n minus 2 minus 1, that's n minus 3, n minus 4, and so on, all the way to 0, okay? Okay, so let's see how we can use this. Are you guys still typing this up, or did you copy it from the website? Who's still working on this? Okay. All right, so let's do the example we did in class. It was this example. we had the main diagonal was 2, 2. Actually, okay, there you go. The main diagonal was 2, 2, minus 1, minus 1. Okay, so what I'm going to do here, I'm going to press Shift Enter. Okay, and then main diagonal is simply 2, 2, minus 1, minus 1. You can use these as lists or as NumPy arrays. Okay, it doesn't matter. Let's just do them as lists now. And then the upper diagonal was minus 3, minus 1, 1. Make sure you put everything in the correct order. So we had minus 3, minus 1, 1, and then 1, 4, 2 for the lower diagonal. L is equal to 1, 4, 1, 4, 2. Okay? And then B, which was the right-hand side, was minus 4, 2, 9, 2. Okay? Minus 4, 2, 9, 2. And I would honestly put the decimal points. I did get an error, actually, in this problem. Questions? Yeah.
You still have an X in there instead of.
Oh, yeah, yeah. Thank you. Good catch. Thank you. 0.0. Okay. So now how do we call the Tomas algorithm? Simply say, solution or whatever variable x, whatever you want to call it, solution, sol is equal Tomas. You call the Tomas algorithm. What does the Tomas take? Lower, main diagonal, upper diagonal, right-hand side. I'm just going to pass them as is. L, D, U, B. Now I claim that solution is going to contain the solution. 1, 2, 3, 4. What is the order of the solution? It's going to be the way you put in your matrix. X1 is going to be 1, X2, 2, X3, 3, X4, 4. Okay? Now, how do you validate your solution? You use the built-in solve command, okay? But the built-in solve command from numpy.lin algebra is going to require a full matrix. How do we create a full matrix? From diagonals. That's where the diag function comes in, okay? So what I'm going to do is declare a full diagonal, and then mp.diag. For the lower diagonal, it's going to be located at minus 1, plus mp.diagonal. For the main diagonal, it's going to be the main diagonal, so k is equal to 0, plus mp.diag. For the upper diagonal, it's going to be located at 1. Then you can print a to validate, okay? Oops, okay. So what happened here? This is obviously not, these are obviously not the main, not the diagonals that we declared, correct? Because our diagonals were 2, 2, minus 1, minus 1. Look at that. We have 2, 3.5, 0.14, minus 15. What happened here? Remember what I mentioned about, yes? No, so no. What happened, we passed the variables without making a copy of them. So Python changed the original value. So what happened here, when I made the call Tomas and I gave it L, D, and U, well, inside Tomas, it took L, it took D, and it took B, and it changed them. And because we didn't make a copy, it changed the original values as well. Okay? So what we could do is either make a copy inside the Tomas algorithm, okay, to make sure we don't commit this error. So you could do over here, give it a different name, okay, and then say L is lt.copy and D is dt.copy. So make it true copy. U is ut.copy. And then B is bt.copy. T is for temporary. Okay, so now let's re-execute again and again. Now let's see. Okay, look at that. See what I did? So when we first passed the variables to the Tomas algorithm, we didn't make a copy. We just passed the variable name. It still points to the same location in memory. So when we modified it inside the Tomas algorithm, it modified that memory. It's not because they were called the same. We could have called this, DA, UA, LA, BA, okay? And then LA, DA, UA, BA. The name doesn't matter if you didn't have this copy over here, okay? If you did not have this copy, and then you call Tomas, and then you print DA, look at that, it changed it. Because it took a reference, it changed the original memory, okay? So that's one of the pitfalls you have to be careful about. If you don't want to change your original variables, which is what we wanted in this case, make a copy.